Okay, this one I'm just going to kind of wing it. I mean, it's important. But let's say this represented a roller coaster, and actually I'm gonna move the whole thing. I'm gonna move the whole thing to the right, actually. Okay, let's say this represented a roller coaster, and let's say they did indeed dig a hole in the ground, which they did in Disney World. They have roller coasters that go into the ground. But let's say you were interested in this roller coaster when it's above 2. Let's doesn't matter if that's 2 meters, whatever. Let's just say it's a scary ride instead of a fun ride. And you're interested in this roller coaster when it was above 2. And the roller coaster ride only lasted 6 minutes or something like that. Let's say 0, 0 is smaller than x is smaller equal than 7. Yeah. Yeah, let's go with 6 so that we can see it. Where is it? Smaller equal. Let's go with 5 so we can see it. 5's too little. Let's stick with 6. Okay, so there's our roller coaster ride. And we were concerned with what spots of the roller coaster are above 2. Well, let's start with just above the ground first. It's really easy to figure out what's above the ground when you know your curve, even if you're not given this information. Suppose you were just given the intercepts, right? Suppose you're just given the intercepts. Well, you say to yourself, okay, I don't know the graph yet. But you say to yourself, okay, when this multiplies out, it's clearly a cubic, because it's x times x times x. That's always how you figure it out, by the way. And it's clearly a positive in front of it. So which means you know that it's going to start in quadrant 3. It might go through the x-axis 3 times maximum, and up to here. And that's the nature of a cubic. It can't go through the x-axis more than 3 times. And the only other time it can do 2, where it just touches, or it can do 1, where it doesn't only go through once. But you can quite clearly see the x-intercepts. Now, obviously, most of your problems are going to show the expanded form, and you have to figure out the factors using synthetic division. But you can quite clearly see that this goes through 1, 0, 3, 0, and 5, 0, right, from this. And since you know that it starts in quadrant 3, you automatically know it must go up through the leftmost x-intercept first. And then since it's going through this, it must come down and it must come up, because that's the nature of cubics, and you should learn that. You should learn the nature of cubics. And clearly, since the x-axis represents the ground, you can see that in this stage here, it's above the ground. And in this stage here, after 5, it must be above the ground. So you can instantly say between 1 and 3 seconds, it is above the ground, and from 5 to 6 seconds, because the ride only lasts 6 seconds, it's above the ground. Great. That was easy enough. But sometimes they're going to ask you, well, when is it 2 meters above? Okay, now, they're never going to make it this mean. They're always going to make it, let's see if I can, they're always going to make it nice and clean like that, right? All I did there was raise my graph up 2. They're going to show the expanded version of this, and I should actually show the expanded version to you. So what is the expanded version of x minus 1, x minus 3, x minus 5, and then I'm just going to add 2 to it, and I'm going to get them to expand it for me. Nice thing about Simulab, and they come up with this nice little cubic right there. So this is the actual graph they're going to give you instead of the nice factored one. They're going to say, oh, okay, here's your cubic representing the roller coaster, and they're going to say, when is this cubic above 2? And the solution is, and you might say, well, geez, I don't know. And when you factor this out without the 2, you're going to discover, oh, those aren't clean at all. I can't factor this at all to figure out the x-intercepts. So I don't know how I'm going to figure this out, because I don't know how to graph it or anything. But you're going to discover the secret is, first, you're trying to get this whole equation equal to 0. So your first step is going to, and just you're going to remember you're looking for above 2. But you're going to start with making it equal to 2. Then you're going to subtract 2 to the other side. So you're going to get minus 2 is equal to 0. Okay, and then you're going to say, okay, well, minus 13 minus 13 minus 2 I'm left with minus 15 is equal to 0. And then they're never really going to give you a question that's tough to factor, because they might if they let you use graphic calculators or a formula calculator. But you're going to quickly discover that whatever they give you, if you put in a factor of 1, like we're going to try synthetic division of 1 here. We're going to go the long route. And I know you can already see what's going on. So the factors here are 1, minus 9, 23, and minus 15. And you do your synthetic division. And you discover minus 8, and you do your synthetic division, and you add that, and you go, oh, that's 15. And then you go, oh, that's a factor of 1 is 15. And I'm left with x plus 1, or x minus 1. And suddenly I got 1x squared minus 8x plus 15. What's a number that adds up to plus 15, multiplies out to plus 15, but adds up to minus 8? You quickly go, oh, wait, that's clearly minus 3 and x minus 5. And you're going to discover most of your questions are like that. So now you have this lovely factored thing. And you say, yeah, but this is now equals 0. I was looking for a bigger than 2. Well, by subtracting the 2 to the other side, you've essentially taken the roller coaster that was at 2, and you've brought it down to the x-axis. And so now the x-axis is actually where 2 used to be. You know, that's what happens when I simply added 2 to this equation to get it nice and clean. In reality, I should have had the formula that I expanded to, which is x cubed minus 9x squared plus 23x, was it? Plus 23x minus 13. Now, it's clear that's the same graph, right? But you wouldn't know that. You wouldn't know that from expanded. And it's clear that if you knew how to graph it or could graph it, you could see all the clear points where it's above 2. But by taking this whole graph and lowering it by 2, we've put it down at the x-axis, but those spots are actually the same spots that you were looking for when it was higher up. See, that's why you're making everything equally 0, so that it's factorable, and you find what's on the x-axis. But essentially, by lowering this entire roller coaster by 2, this green line becomes the x-axis and allows us to factor it. And that's what you're doing. And then quite clearly, you're able to do the same process again. Say, okay, well, this roller coaster is above the ground between 1 second and 3 seconds, and between 5 seconds and 6 seconds, and everything, or above 2 meters, or whatever they're looking for, rather, and everything else it's below 2 meters. They don't even care what it's below unless they want you to say what's the max and what's the min of this roller coaster, and then you'd have to take derivatives to find the max and min. But again, they're going to make things solvable. And that's it, and it looks more complicated than it is. So this entire chapter is about different methods of factoring. Which page was I on? I'm on page 225. Finding when two polynomials are unequal. And yeah, they might make it hard on you. They might say, okay, well, I've got this polynomial here, and this polynomial here, whatever. And they might say, when is this polynomial above that polynomial? And it's the same process. You bring it all to the other side until it equals 0. Then you solve the factors, and then you have to then use graphing tables and say, okay, if I wanted to know when they were when this thing was above this, I need to have an idea of some values, because once you find the x-intercepts again, you'll know when they cross. So let's say these two graphs did this. Let's say one did this in black, and one did this in red. And I'd say, when is the black line above the red line? Well, it's clear that the black line is above the red line here, and it's clear it's here. But when you find those x-intercepts, which is all factoring gives you, it'll give you these points here where they cross, you won't know where it is until you construct a table and say, okay, what's going on in this interval? Okay, the red line has y values that are 2, and the black values are 7. So it's clearly the black line is going to be above the red line in those intervals. And you keep doing it for each interval. It's the same way you would do a graph. And that's all this chapter does, and it goes through techniques, mostly synthetic division techniques, of solving these situations. And a lot of it's going to be synthetic. It usually combines all the tools you've learned last chapter, which is why you can't skip chapters and hope to stay ahead in math. And then it goes through other methods. You can do a factor table. And if it allows you to use a graphing technology, you can use graphing technology. And then it'll even sometimes look really complicated. But just remember, you can usually get rid of these. So here's the same thing. They're asking us, here's a roller coaster. When will it be 9 meters above ground? Now, it's clear in the graphing calculator. That's when it's 9 meters above the ground. But you won't be able to do anything the way it is now. They first, well, they're using a graphing calculator, so it's kind of cheating. But if you couldn't cheat like that, and it looks like their answers are not pure, so you wouldn't be able to factor. So when it's not pure, you do indeed have to use a graph calculator. But normally what you do is you'd make hx equal 9. You'd bring this 4,000 over, multiply the right side by 4,000, and get 4 million times 9. And then you'd have to then bring that number over here. You'd have to expand all of these, add all your like values, and then try to factor it using synthetic factoring. Now in this case, they said, this is an unfactorable one. That's why you have to use graphing calculators. And then it goes through what you need to do. And then you're just essentially saying you got to move everything to the one side of the equation, make it equal to 0, determine all the zeros, and then figure out using a number line where it's above or below the number you're trying to find. And then they go through the other methods. So here we go. Check your understanding. Using a number line strategy, express the answers in set notation. And they said you want to know when these numbers are above or equal 0. Well, we can easily see when they're going to be equal to 0. Okay, and I'm going to just focus on number 1 here. We can easily see when they're going to be equal to 0. They're going to be equal to 0 when x is minus 2 here, when x is 3, and when x is minus 1. But the question is, if I was going to do a number line there, I have to say, and you should put them in order, so it goes minus 2, minus 1, and 3. I have to determine what's going on in between here, what's going on to the left of 2, what's going on in between here, and what's going on to the right of 3 to figure out when it's above 0. So you would take any number. You'd take minus 3, which is to the left of minus 2, and you'd plug it in. But you don't have to solve it. You just have to keep track of what's negative and what's positive. Minus 3 plus 2, negative. Minus 3 minus 6, negative. Minus 3 plus 1, negative. A negative times a negative times a negative will be negative. A negative number is not above 0. So I know that this entire section is not above 0. I also know the nature of cubics. Since it has 3 intercepts, this section here must be above 0. This section below must be below 0. And this section above must be above 0. However, if I'm going to do the number line strategy, we would indeed take a number in between minus 1 and minus 2, like minus 1.5. And you'd do the same thing on the left. You'd say, okay, minus 1.5, this becomes positive. Minus 1.5, this becomes negative. Minus 1.5, this becomes negative. Positive times a negative becomes positive. So we indeed figured out that's good. If I was doing number line here, the easiest number for me to use is 0. I get minus 2 times minus 3, that's positive, times plus 1, that's negative. It's quite clear that this whole zone is not good. And the easiest number for me to use here is 4. 4 minus 2 is positive, 4 minus 3 is positive, 4 plus 1 is positive. It's positive. So right now, I can note it this way. I can say when minus 2 is smaller or equal, because it's bigger or equal to 0, than x, and smaller and equal to minus 1. Or when x is bigger or equal to 3, the function in A is above or equal to 0. And that's how you would answer. Now in set notation, in the other notation, you would do it like this. You'd include the 2. You go minus 2, minus 1, and you'd include the 1. And then you'd also say the other one you would include, comma, and then you do the positive infinity sign, and you do a rounded bracket for that one. And that's because infinity is never included in the notation. And that's the other way you do notation. Now I'm just going to do the x values, but you can do it whatever they ask for. Now, the interesting thing about this one is the minus 2 will play a factor because it's multiplying all the things. So this tells me if I multiply all the x's, I am indeed dealing with a cubic, so that helps in my knowledge. But I'm also dealing with a negative 2, which will be an inverse cubic, which means it's going to start in quadrant 2 and end in quadrant 1. Since I can clearly see there are 3 intercepts, I can clearly see everything to the left of the first intercept is positive. This time we're looking for everything below 0. I can see that this area is below 0, and this area ever after this intercept will be below 0. That's using logic. You won't always be able to use logic, and here they want you to use a number line. Well, the number line tells me that when, and I'm just going to get rid of some of the scratches, there we go. The number line tells me that this goes through 2, 0, 4, 0, and minus 3, 0. So I want to put it in order. So minus 3, 2, and 4. But I have to remember that when I'm testing my numbers, I have to multiply by minus 2. So let's take a minus 4. So minus 4 here is minus, 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 but times a minus. So minus times a minus times a minus times a minus is positive. But I'm looking for below 0, so I'm not looking for that zone. Clear to me that this is going to be in the zone, but we're going to take a number between 2 and minus 3, and the easiest one is 0. So we're going to take 0, and we get minus times a minus times a minus times a plus. And so that means that this is indeed one of the zones I'm looking for. I know it's going to be positive here, but I'm going to take a number in between, which is 3. So I get a minus. 3 minus 2 is positive. 3 minus 4 is negative. And 3 plus 3 is positive. So I get a negative times a negative. Sorry, negative times a positive times a negative times a positive. It ends up positive. So that tells me this zone is positive, and it's not what I'm looking for. And I take a 5 to see what happens beyond. I get a negative, positive, 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 which gives me negative. So everything after 4 is what I'm looking for. So that means the zones I'm looking for are between minus 3 and 2, and everything above 4. Writing in notation, I would say minus 3 is smaller than x and smaller than 2. Why do I say that? Because they're looking for things that are smaller, not smaller or equal. And then I would also say when x is bigger than 4. And then you can end it with a sentence that says, is when the function in b is below 0. And that's pretty much how you do it. Pretty easy after that. So I'm going to get rid of those. The lines are a little different. See, the intercepts here are 3, minus 2 over 5, and 3 over 4. And you simply do that by making this equal 0 and solve for x. Doing on a number line, in order, I have minus 2 over 5, 3 over 4, which is 3/4, and 3. So that's in order. Now the nice thing is you can take clean numbers. 3/4 is positive. This is negative. So a nice clean number in between is 0. A nice clean number to the left of minus 2/5 is minus 1. A nice clean number between 3/4 and 3 is 1. And then you'd use 4. So we're going to test for minus 1. I already know that just by my knowledge of cubics that this is a positive cubic. So since I'm looking below 0, I know that it's going to go up like this, come down, go up. Sorry, it's going to go up like this, come down, and go up. And I already know that since I'm looking for smaller than 0, I know it's going to be to the left of this. It's going to be between these. And that's just knowing it. But using the number technique, I take minus 1 and put it in here. I get minus 5 plus 2, minus 4, minus 3, minus. So it's clear that this minus times a minus times a minus will be minus. So everything to the left here is minus. If I take 0, I get minus 3 times plus 2 times minus 3, which is a positive. So it's clear that everything between here is positive. When I take 1, I get minus, positive, positive. So I get everything in between here is minus. And then when I take 4, I get positive, positive, positive. So everything after 3 is positive. So I definitely find out that the zone I'm looking for is between 3/4 and 3, and everything below minus 2/5. So I would say when x is smaller, not equals, because I'm looking for anything below 0, not below equal, or when 3/4 is smaller than x is smaller than 3, then the function in C is below 0. So they're just training you to understand how to figure out, using number lines, how to figure these things out. What about this last one? Well, I can see when x is 5, this is going to be 0. When x is -1/4, this is going to be a 0. And when x is 5/2, which is roughly 2.5, this is going to be a 0. So constructing in order on a number line, I get -1/4 is the lowest number. 5/2, which is 2.5, is the next lowest number. Now your teacher might want you to keep it in fractions, but I'm just doing it here for this case. An easy number to the left of -1/4 is -1. An easy number between these two numbers is 0. An easy number between these two numbers is 3, and then I use 6 afterwards. So if I use -1, this becomes minus, this becomes minus, and this becomes minus, which means everything after this, everything before this, let's try that again. -1 will become minus, this will become minus, and this will become minus. So minus times a minus times a minus means everything to the left of this is minus, which is not what I'm looking for. I automatically know that I'm going to be looking for this and everything above 5, but I'm going to go through the process anyway. When I put in 0 here, I get minus, positive, and minus. So clear that when I'm at 0 or in between these numbers, I'm going to be positive, and that's what I'm looking for. And then when I put in 3, I get minus, positive, and positive. So it's clear that when I'm looking at those numbers, they're all going to be minus. And that's because once it crosses the x-axis, all numbers between there will behave the same way. And then finally, if I look at 6, I'm dealing with positive, positive, positive. So I'm looking for positive. Since my question is asking for positive 0, I can say that between -1/4 and smaller or equal to x, because I'm including 0 this time, and smaller or equal to 2.5, and when x is bigger or equal to 5, the function in D is above or equal to 0. Not too hard. For each graph, determine when f of x is below 0. Express your answer using. Now this is just very easy when you have a graph. Whatever number they're looking for, you can just draw a line. This one here touches right there at 1. So the only time it's below or equal to 0 is at that specific point. But for this first graph, I can see it's below 0 here, so when x is smaller than or equal to -5. And I can see it's below 0 between -2 and 0. And I can see it's below 0 after 3. So I would write that as x is the function in A is below or equal to 0 when x is smaller or equal to -3, or when -2 is smaller or equal to x, smaller or equal to 0, or when x is bigger or equal to 3. And those are all the times that this graph is below 0. And all they're saying is, when is this graph? When are the y values 0 or negative? That's all that means. What about this one? Well, like I said, it only hits 0 once. So that's when x is equal to 1. So that's the only answer for this one, because they've included 0. Pretty simple when you get used to what they're looking for. Do the same thing in this case. They're looking for 0, so just draw a number line. They're looking for it's below or equal to 0. And I'm not going to do the notation anymore, but I will show you it's below 0 between -7 and -3, which is there. And it's below 0 between 0 and 4, which is there. And you just write it with that x. Since they're looking for below and equal, you'd say -7 is below or equal to x, is below or equal to -3 is one of the intervals right here, and etc. for this one. What about this one? Well, it's clear on this one that the graph is below 0 to the left of -4, so when x is smaller or equal to -4. between 2 and 7. So when 2 is smaller or equal to x is smaller or equal to 7. Everything else is positive, so I don't care about that part. You might say, why do you need this? Well, in science, you definitely will always look for conditions within certain criteria. For instance, when can I expect the polar ice cap to melt? What seasons based on what temperature changes? Things like that. Or at what point will the bacteria overwhelm the body and kill the host? You know, when we have to get to it. And by the way, sepsis, which is when the body gets infected in the bloodstream, is incredibly dangerous. There's huge science in studying infections, both viral and bacterial, and knowing growth rates of certain bacteria. And as life progresses, you'll have new bacteria that's more aggressive, especially as they get stronger against antibiotics. And so studying these things is important. If you leave an infection too long in your tooth, it goes to your brain, and it could be too late to cure it. So all math touches on all subjects. As Neil deGrasse Tyson says, it's the language of science. Here we're doing number 3 here. So this is a great example. They're saying, when is this function above this function? Now, we know they're both cubics. This function is, slightly different, but we need to know when they're above one another. Well, let's write that out. When is this function above this function? Well, the secret is getting everything to one side and having it above 0 on the right side. So when I bring over the x cubed, I'm left with just 1x cubed. When I bring over the 3x squared, I get minus x squared minus 3x squared. So that becomes a minus 4x squared. When I bring over the 2x, it becomes 3x minus 2x, or just 1x. And when I bring over the 4, the 10 becomes a 6. So I've got this. So now, and it's equal to 0, bigger than 0. So now I just set it equal to 0, and I try to find out if there's any x-intercept, because essentially I've subtracted two functions, and whatever's left over will be above the x-axis or below the x-axis. And you could graph this. Oh, and it says using a graphing calculator. So now you would put this into a graphing calculator. X cubed minus 4x squared. Plus x plus 6. And usually they ask you to do this when it's not clean. Now, I don't know why they didn't want us to factor it, because those are clean factors. And remember that we're looking for when this function is above 0, or in other words, above the graph before. So it's clear that this function is above the 0 mark between minus 1 and 2, and between 3. However, you could have also used, and I think they're just getting you to practice graphing, you could have used synthetic division. The numbers in front of it are 1, minus 4, and 1 and 6. Now, we would have started with positive 1, but then we would have moved on to negative 1, which is x minus 1, or sorry, x plus 1. And we would have used graphing, synthetic calculation, and we would have discovered we came up with it when it was minus 1. In other words, when x plus 1 was a factor. And that would have left the graph x squared minus 5x plus 6, and we would have quickly seen that that's minus 6 plus 1. Then putting in order, and did I get it right? I got it. Minus 6 plus 1. No, I got it wrong somehow. So I know that minus 1 is indeed a factor. And then when I'm left with x squared minus 5x plus 6, oh, it's got to be two numbers, sorry. So it's x minus 2 and x minus 3. Putting that in the right order, well, actually it's in the right order right now, I would discover I could graph it very much like this. It goes through minus 1, it goes through 2, and it goes through 3. Now I also know this is a positive cubic, so it's going to come up, down, and up. And so now I know that these are the areas above 0 and everything here. So right away I know that when minus 1 is smaller or equal, and they only, not equal because I want it above only, x or smaller than 2, or when x is above 3, f of x is above g of x. And you might say, no, you didn't do that at all. All you did was solve for this cubic here, which has nothing to do with the other cubic. No, just like when lines intercept other lines in only one spot, when we put the original graph in here, which is x cubed minus 7x squared plus 4x, and we put the second graphic in there, x squared minus 4x minus 9, which is a parabola, it becomes clear that, no, hang on, let me make sure I got it right. X cubed minus 7x squared plus 4x plus 12 is bigger than x squared minus 4x minus 9. So we're going to just put in an x is equal to minus 1 and see. And actually that doesn't quite work. It should have been here. So that means that either I did a, oh, I know, wait, look what I did wrong. I was subtracting x cubed from the x cubed, which is not the case. So it was not easily factorable. Sorry for wasting your time. What I should have been left with is x cubed minus 7x squared minus x squared is minus 8x squared plus 4x is plus 8x, and then plus 12 plus 9 is plus 21. Oh no, that's not the one I was solving. I was solving the other one. Let's see if I got the other one right. Looks like I have to go back. Yeah, so what happened here is I put the wrong, I was working on 3 and I put 4 into Desmo, so sorry, that's all over the map on that one. Okay, so I'm going to go back to this. And this is the one I was supposed to put in Desmos. So I get 2x cubed minus x squared. So 2x cubed minus x squared plus 3x plus 10. When is this function above this function? X cubed plus 3x squared plus 2x. Plus 2x plus 4. Okay, and clearly enough, I'll just get rid of this x is equal to minus 1. We can see it's the red graph is above the purple graph there. Then the purple graph seems to take over. And then somewhere the red graph takes over again, or the other graph takes over again. It's easier to see if I put in the factors I discovered. X is equal to, or x equal to minus 1, x is equal to, what were the other factors I discovered? Was it 3? I forget the other fact. Oh yeah, it was minus 2, or 2, and x is equal to 3. And then when you go up, you can see that's when the purple graph crosses over. And then when you go up, you can see that's when the next, well, somewhere there, yeah. You might say, well, no, red line's over here, but you have to go look above. You can see the red line's going to be way above it at that blue line. And then at this red line, and I should actually not make it red, I should keep all these black. There we go. You can see at this other one, right there, if you zoom in, that's when the purple line started going above the red line for just a little while. See, the purple line is above the red line. You know, graphically, this was pretty hard until we subtracted it, and then we were able to determine it. It's much clearer at this other line here, minus 1, that the red line is, at that point, the red line is above the purple line. And everything below, to the left of that, the red line is below it. There you go. Now, not all cubics cross 3 times, but they often will. So moving on to number 4 here. Sorry I kind of botched that up, but that's just from the numbers I put in the calculator. Solve this inequality. It's the same thing, except this x squared will apply there. So I'm left with x cubed. Oh, this one wanted us to use the graphic calculator. Minus 8x squared plus 8x plus 21. And they're saying, when is this all bigger than 0? And I know they want to find bigger than 0 because it says bigger than here. So you just set it to 0, and normally you would see if it's solvable, but they say use a graphic calculator. Get rid of all these. And we're just going to see where this function crosses the x-axis. Which is a lot easier than trying to see where the graph crosses. Now, the reason they wanted us to do that because the only clean factor is the 3. And then you have to go back and say, did they want to know when it's above 0? Yeah. So that means between minus 1.14 and 3, it's above 0. And then above 6.14, it's above 0. And you can see that studying this one graph is a lot easier than studying the two graphs combined. Look at the two graphs, 4x plus 12 versus the parabola, x squared minus 4x minus 9. They both minus. Well, you can also see, okay, that's when they have a cross point, that's when the red gets above. That's also when the cross point, that's when the green gets above. And there's our other cross point when the red gets above again. And the only clean point is here at 3. But visually, you know, it's a little bit harder to see where that happens. It's a lot easier to solve it. And if they let you use a graphing calculator, even easier. Okay. For each of these, state the intervals where x is above 0. So again, it's quite clear that it's between minus 1 and 2. And you'd have to say smaller because they're looking for only above, not equals. And that's clearly when x is bigger than 4. And you do that for all of them. A little tougher to see on this one. You have to assume they're giving you clean numbers. When is it above 0? Every time x is smaller than minus 2. And between looks like, so above 0 it looks like only here. Between 0 is smaller than x is smaller than 1. And the rest of the times it's below 0. What about here? This is kind of nice. It looks like when minus 2 is smaller than 2, then smaller than x and smaller than 2. And then it bounces off 2. So actually you would not say smaller than 2. Oh yeah, you would have to because it touches 0 there and they don't want 0. So then you say also when x is bigger than 2. Now if they wanted to equal 0, you wouldn't need this extra thing. You could just say is smaller or equal than infinity. Or even better, you could just say x when x is bigger or equal to minus 2. But because they don't want the 0, you must exclude that point there. Okay, moving on. When is this bigger than 0? You might be tempted to say all of them. But no, it touches 0 there. They don't want that line. So you could either say when x does not equal 2 and all other points are fine. Or you could say, stupidly you would want to, when negative infinity is smaller than x is smaller than 2, and when 2 is smaller than x, it's smaller than positive infinity. But it's a lot easier to say when x does not equal 2. Okay, solve the following inequalities. So this just would be using a number line again. So for A, we're looking at a parabola, and it clearly goes through 1 and minus 1. If you know your parabola, you also know this one's positive, which means it's upward facing. Since it goes through -1 and 1, it goes like this. Since they're only looking for when it's above 0, it's only above 0 to the left of -1 and to the right of -1. So when x is smaller than -1, pardon me, or when x is bigger than 1. And they only want bigger than. See, it's not bigger or equal, it's only bigger than. This is just logic and graphing and knowing your graphs. This next one is also a parabola, makes our life easier, but this time they want to know when it's smaller than 0. It has also got a positive leading coefficient because x times x is positive x squared. It goes through -3 and +4 is upward facing. And the only times it's below 0 is between -3 and 4. It doesn't count -3 and 4 because they want below 0, not touching 0, which means -3 must be smaller than x must be smaller than 4 for this function to be below 0. Next one is also a parabola, but it's a little bit trickier about what the intercepts are. The first intercept is -1/2. The second intercept is 5. But when I were to multiply 2x times x, I get a positive 2x squared, which means this is an upward facing parabola. They're looking for bigger or equal to 0. Well, it touches x-axis, which is equal to 0 at -2, and it's above 0 ever after. So when x is smaller or equal to -1/2, it touches 5 and is bigger ever after. So when x is bigger or equal to 5. And those are the two spots where this graph will be above 0. The next graph looks like it might be a parabola, but this -3x multiplies this x, and it's -3x cubed, which means it's an inversed cubic, which means it starts there, crosses x-axis, goes up above, and negative. Now, it helps me a lot better to know the graph than doing the number line. And I can tell you from this graph that it's going to go through 0, 0, right there, 0, -7, and 2. So that means my numbers in order are -7, 0, and 2. Since I know this is going to be a negative 3x squared, I know I start up here. I have to go through -7. I have to go through 0. I have to go through 2. Since I'm looking for below 0 and not equal, I'm looking at this area and everything after 2. So I'm looking for between -7 must be smaller than x, smaller than 0, and every time x is bigger than 2, this graph will be below the y-axis, which means below where will y values be negative. Everywhere below the x-axis. Okay, and that's all this means. Where will the y values be negative? Okay, this one is a little bit more complicated, isn't it? Because they're adding two graphs, and it looks like I accidentally deleted. They're looking for above or equals to 0. I accidentally deleted it when I erased this graph. But they're looking at two graphs, which means I have to expand it. I can't just look at these two graphs. I have to add them. The first expansion is x squared minus 2x minus 3. And then I'm going to add everything in the bracket, which is x squared plus 2x minus 3x minus x minus 6. Which means I just add or subtract them. I actually didn't need a bracket for the add. So I'm going to get, when I add the common terms, I get 2x squared minus 3x plus 18. And you have to ask yourself, and you always got to make sure your math, make sure you did it right. Minus 3x plus 2x is minus x. Minus 6, yeah. X squared, yeah. X squared minus 3x plus 2x plus 1x is minus 2x and minus 3, yep. So, and then make sure you added all your terms correctly. Oh, see, look at that. I multiply the minus 3 times minus 6. It's really just minus 9. Which means that you're looking for a number that multiplies out to minus 18, but adds up to minus 3. Which means those numbers are going to be close together. One's going to be positive and one's going to be negative, because that's the only way you can get a negative number. And it looks like it's going to be 6 and 3, but it's going to be positive 3 and negative 6, which add up to negative 3 and multiply out to negative 18. I'm going to use the slip and slide method, which means I'm going to do x plus 3, x minus 6. I'm going to slip the 2 under here, which means that this last one just becomes x minus 3. The 2 cannot be divided into 3, so it means I have to slide it in front of that. And if I expand it to make sure, I get 2x squared, check. Minus 6x plus 3x, which is minus 3x, check. Minus 9, check. Which means my x-intercepts when I added these two functions is when x is minus 3 halves and when x is 3. Since this is a parabola, it goes through minus 3 half and 3. It's also a positive parabola. There's a positive leading coefficient. It's also looking for when it's above and equal to 0. So it's anything to the left and anything to the right of those numbers, which means it's going to be positive when x is smaller or equal to minus 3 halves, or when x is bigger or equal to 3. Now I'm going to do this last one, and then I have to take a break. And you have to expand it again. So you get 2x squared plus 8x. Now, it's important for me to keep track of those negatives. So it's minus 3x squared minus 12. So 2x squared minus 3x squared becomes minus x squared. And then, oh no, 2x squared is all alone. That's not x squared here, so I did a mistake here. That's just 3x. So it's clear that it's going to be 2x squared plus 5x minus 12. So your only question is, since they're looking below or equal to 0, is there any number that multiplies out to negative 24 that adds up to 5? It's going to be a positive and a negative number. So there's 6 and 4, that won't do it. There's 12 and 2, that won't do it. At this stage, I want to make sure I got my numbers right. 2x squared plus 8x minus 3x, yeah, minus 12, yep. So, minus 24, but adds up to plus 5. So, 8 and 3, there we go. So, we're going to look at 8, positive 8, minus 3. Those multiply to minus 24, that add up to 5. I'm going to use the slip and slide method, which is just put the factors in, but then take the leading number here and divide each number. 8 divided by 2 is 4. 3 can't be divided by 2, so I slip it in front of the x. So I'm left with x plus 4 and 2x minus 3. And to make sure, you multiply it out to see if you got you get this parabola here. 2x squared, check. Minus 3x plus 6x is, minus 3x plus 8x is plus 5x, check. Minus 12, check. So this is the factors, which means if I do a number line or it's a parabola, I see that it's going through at minus 4, 0 and 3 over 2, 0 or 1.5. Since I'm looking for when it's below or equal to 0 and it's a positive parabola, that means it's going to be facing upwards. I know it's going to be below or equal between those two numbers. So when minus 4 is smaller or equal to x is smaller or equal to 1.5 is when this whole thing is smaller or equal to 0. That's how you do those simple ones, and they're going to give us some tough ones.